Hi folks, we're looking at page 582 number 6. So they give us this function here and they want us to determine where the slope of the tangent is 0. So in other words, we need to determine where the derivative is equal to 0. So again, as soon as you notice a function where the base and the exponent both contain a variable, then you know that you can't use either derivatives of exponential functions or power functions. So you're going to have to use what we call logarithmic differentiation. In other words, take the logarithm of both sides before differentiating. Okay, so let me take ln of both sides. So here I've got ln y equals ln of x to the 1 over x. Okay, now often you can skip this step because you know that you're going to be using the ski-slope rule on the right-hand side. So here we've got ln y equals 1 over x times ln x. And of course, the reason why we took the logarithm both sides was in order to use this ski-slope rule. So now you've got these as two separate functions. Okay, so the trick here is to now take the derivative of this side, but you're not taking the derivative of y, you're taking the derivative of ln of y, so you need to use the chain rule. Okay, so you can think of it as first taking the derivative of ln y with respect to y, which is just 1 over y, then times the derivative of y with respect to x, which I can just denote by y prime. So we'll assume that y prime represents the derivative of y with respect to x. Okay, if you're not comfortable with that, just write dy dx instead. Okay, so in other words, this function y acted like our intermediate variable u. Okay, so there's the derivative of the left-hand side. Now the right-hand side will have to use the product rule, okay, or we could use the quotient rule. So either way, in fact, I think I'll use the quotient rule. I'll think of this as ln x over x. Okay, so derivative of the numerator is just 1 over x times the denominator function, which is just x, works out nicely, minus the numerator function times the derivative of the denominator, which is just equal to 1. Okay, all over x squared. Okay, so now here, y prime, which is what I'm looking for, the derivative of x to the 1 over x is equal to, so I'm going to multiply this y to the other side, okay, and I know that y is equal to x to the 1 over x. So I'm going to replace y now by what it's defined as, x to the 1 over x, and let's simplify this thing here. Okay, so this just becomes 1 minus ln x, okay, over x squared, and so y prime is equal to x to the 1 over x times 1 minus ln x all over x squared. Okay, so now we need to determine when this thing is equal to 0. Okay, so x to the 1 over x can't ever be equal to 0. So here if you replace x by 0, you also have 1 over x, 1 over 0, and that gives you a problem. So it's undefined at x equals 0. So that means the only place where this can be equal to 0 is when ln x, when 1 minus ln x is equal to 0. So in other words, when ln x is equal to 1. Okay, now hopefully you should know that this is going to occur when x is equal to e, but just in case you don't think of that, you can always actually solve this. So how do I get the x out of the natural logarithm? I use its inverse function, so I take e of both sides, and this just becomes x equals e. Okay, and so there you have it. This function here will have a horizontal tangent at x equals e. Okay, that's it for this one. By the way, if you want to check it out, you should graph it on Desmos and